Hello everyone and welcome back. So, to start things off on this lesson here, I'd like to take a look at these. I'd like to determine the solution set for each of these following open statements. So again, you may recall from our previous lesson here that an open statement was a statement that we don't know whether it's true or false because there's some sort of variable here. So now we want to determine what would make these true. Okay, so take a minute, pause the video, and try to go ahead and determine what should fall here. Alright, so in the first situation here, right, if it's a suit and a standard deck of playing cards here, now, French suited, I'll explain that later on, you'll note that there are only 4 suits in it, there are 4 types, right? You have your spades, you have your clubs, which kind of look like this here, I'm really awful at drawing them, those are your black suits here, and then you also have your red suits, the hearts, and you also have your diamonds. And those are the 4 suits, and these are the 4 objects here that belong to the solution set. In the second case, this is a borough of New York City. I think we can all very easily label them here. We can mention this. We have Queens, which is where I hail from. You have Manhattan. You have the Bronx. You have Brooklyn. No sleep till then. And then you have Staten Island, which a lot of people seem to forget about for some reason. I don't know why. So you'll note that in this situation, there are only 5 boroughs of New York City, unless, Mayor de Blasio does something that he hasn't announced recently. Interesting. So we have this here, much like how here we have a set of 4 objects in this solution set. In number 3, x is an integer and 0 is less than x is less than 4, I think we can see here it's pretty clear that there are only 3 objects in the set. 1, 2, and 3, right? Now, why isn't 0 in the set? Well, note that 0, in this case, these inequalities here happen to be strict inequalities, so you're not allowed to include both either endpoint. So 0 is not in it, 4 is not in it as well. Okay, so in order to go on here, I want to take a look at each of these statements here, right? We'll take a look at what's going on here. I'd like you to focus on the third statement here. This third statement is certainly different from the other 2. Well, 1, because it's very mathematical, but 2nd, if you note this here, you'll note that there's something about the 2nd one here. In particular, it seems to be more complex than the first 2, right? Notice on the first 2, we have this, we seem to have that there was only 1 condition to follow here, right? This is a suit and a deck of playing cards. This is a borough of New York City here. However, here we have 2 conditions to follow. We seem to have 2 seemingly independent statements that are glued together here. 2 statements that could have been their own open statements themselves. For instance, x is an integer. 0 is less than x is less than 4. Note that these are 2 independent open statements here. I could have just asked, I could have split these up, and we could have done the exercise with them too. You'll note that those 2 are kind of glued together by a connective word, in this case, and. Okay? So, if you, again, just like what you recall from the previous lesson, you recall that I made this analogy between Boolean logic and arithmetic, right? We saw that the numbers were statements and the operations were, in this case, operators. Now we can take a look at what is known one of the simple operators here, where we can just join 2 statements together and create a third one. So what we have here is this idea of what is known as the and. So this here is what is known as the conjunction. Okay? So this is the first of our major operations here, aside from negation. We have what is known as the conjunction. The key word here is being and. Note that sort of signifies the fact that you're joining 2 independent statements together. The symbol for and, as you can see here, is just sort of a caret symbol. I think it's very similar to the symbol above the 6 on your keyboard here. This represents our and here. Okay. Now the truth table, this is going to be a little bit different here, because if you think about what's going on, note what's happening here in this situation. If we look back at this, right, we see that there are 2 independent statements here. X is an integer, 0 is less than x is less than 4. So since there are 2 independent statements here, our truth table is going to be a lot more complex here. In particular, because there are 2 independent statements, we're going to use 2 independent variables here. We're going to call them P, we're going to call them Q, okay? So in this situation here, for something like this, x is an integer and 0 is less than x is less than 4, we're going to call them 2 things here, P and Q. We're going to look at the truth table for this here. Now, just like before, let's go ahead and construct the truth table. You'll note that we're going to have a P and we're going to have a Q here. Because of the fact that we now have multiple statements here, our table is going to be larger. There are multiple independent statements here, so we want a column for each. And, of course, we want a column in here for the end, at the end, for the statement that we have a target for. If you're not sure about this, again, refer to the previous video here. And you may recall that this, we want to show all the possibilities of possible combinations of P and Q here. Now, given that there are two statements here, we can see that each statement has only two values here. So for instance here, right, with P can either be true or it can be false here, right? So this is our start here, sorry, P, start. Note that here there are two options here, and with each of these, there's two options for each of those as well. So for Q, we can have this here. QP can be true or false, and then true or false here. So note that we can kind of create this little tree diagram here and show that there should be only 4 different possibilities here. There are going to be 4 different cases here for us to take a look at, and each of those 4 cases is going to correspond to a row of the chart here. So we can have one situation where P is true and Q is true. That's our first one here. We can have a situation where P is true and Q is false. We can have a situation where P is false and Q is true. We can have a situation where P is false and Q is false. Alright, so you'll note that these are the only 4 things that are available here. Okay? So we note that in this situation, let's take a look at this and try to analyze this situation here. So let's look at each row one at a time. The first row says that P is true, Q is true. So X is an integer and 0 is less than X is less than 4. Notice that these are both true here. So we want to find a number X that makes P true and Q true. X is an integer and 0 is less than X is less than 4. I think we can see here, for instance, one such example would be X equals 2, for instance, right? Now, it seems pretty obvious that this entire statement here should be true. 2 is an integer and 0 is less than 2 is less than 4. It should be a true statement. It makes sense, right? Now, you'll note that not only intuitively does it make sense here, but there's also something else that you should note here that also lends credence to the fact that this should also be a true statement. Because if you're thinking about this 2 here, note that 2 is not the only number that could work here. 1 could work, 3 could work. Now, where I've seen those numbers 1, 2, and 3 before, they're right here. And this was the solution set to the statement here. So this here was the solution set to this statement here, and as a result, because of that here, we know that because it's in the solution set, it makes the statement true. So this entire statement is going to be true here. So we have true, true, true like this, okay? Now in the second row, X is an integer and 0 is less than X is less than 4. We want an integer. We want something that makes P true but Q false. There are a lot of things we can do here. For instance, we can pick 5, right? 5 is an integer, and 5 doesn't belong here. Note that 5 is not in the solution set here, so that means, therefore, 5 makes the statement false. Right? And again, I think you can do the same thing for the other 2 rows. The third row here, we want Q is true and P is false, so we can say something like, say, I don't know, X is 1.5. 1.5 is not an integer. 1.5 is between 0 and 4, but again, note it doesn't show up in the solution set here, so in this situation, it's going to be false. Okay? And similarly, in the last thing here, X is an integer and 0 is less than X is less than 4 with 2 falses here, right? We can just simply pick that. In this case, we can say X is, I don't know, 6.5, right? Again, 6.5 doesn't show up in our solution set here, so this is also going to be false as well. So what we have here, ladies and gentlemen, is this idea here. We can see that in this case, our solution set for AND, the truth table for AND is actually going to work out really, really nicely here. So our conjunction actually looks pretty nice here. We have this. We note that in this situation, the only way for a conjunction to be true is if both pieces are true. If both individual pieces are true, then you have the entire thing true, and so on and so forth here. Okay, so that's going to be our conjunction for the time being.